Hi, welcome back to the course Foundations for Machine Learning. We are continuing to learn some mathematical foundations. However, today is a fresh start because today we are going to start probability and statistics for machine learning. So this is an introductory lecture to probability and statistics. And the ultimate goal is that when it comes to learning machine learning or data science, you should be very comfortable with the terms, with the mathematics, and with the logic behind probability and statistics. So let's get into that. So first of all, ML, as you might have probably realized, it involves a lot of probability and statistics because you are building mathematical models to make predictions uh, based on the available data. Sometimes you have to take decisions based on this. An example of a decision is, let's say you have a AI based spam email classifier. The AI has to take a decision whether something has to be put as a spam or not spam. It's very binary. But to make that prediction or to make that decision, it's using some mathematical model. It's collecting some data from the email that is coming into your email. And then the spam filter will automatically decide whether something is a spam or not. So the reason why probability and statistics is very important in machine learning, probably the most important concepts in machine learning, is because it is not enough that you simply make a decision in ML. Often, for people to trust machine learning models, you also have to show some degree of uncertainty that you have in your predictions. And probability is basically that branch of mathematics or that area of math that deals with the uncertainty in data. And what statistics help you is when you have a huge data set, statistics help you analyze and summarize this data and extract meaningful insights. Because as humans, we cannot process dozens of data, even let alone thousands or 100,000 data points that you typically see in machine learning. So you cannot process the data unless it is described in a summarized fashion. So statistics help you do this. So in this lecture, we'll be learning very basic things about probability and statistics. It's nothing complicated. So you can stay with me throughout the lecture. And as we progress in the next 4 to 5 lectures, we will learn a little bit more complex ideas within probability and statistics, especially in the context of what is useful for machine learning. Of course, we'll not be learning all the things about probability. It's a very, very big and difficult topic. If you have learned probability in grade 12th, you would know that it's definitely not an easy subject. Students typically tend to score really less in probability. I have seen that very, very often. But we will be learning probability from a ML point of view. So firstly, if we look at certain ML problem statements, I already mentioned the email classifier, classifying email as spam or non-spam. So here, you need the data collected from the email to define a probability for something being a spam or not. And you can define a probability cutoff. And then you can say if the probability of something being a spam is greater than 90%, then take the decision of putting that particular email into the spam folder. Similarly, in weather prediction, it's almost always a certainty. So if I search the weather here, you can see that, let me not, you can see sometimes, see precipitation chance 0%, humidity 41%, wind 26. But if I change it to some other day, so now I have changed it to Friday, you can see that there is a precipitation chance that they are mentioning humidity 55%. Actually, this precipitation chance is it's not like if it's raining, right? This will be 100% at the moment. If it is not raining, it will be 0%. So basically, if I am picking today as Wednesday, and if I look at the precipitation, it will be 0%. But if there is heavy rain, if there is a high likelihood of heavy rain, this number will be greater than 0%. In weather predictions, especially, you cannot say things with great deal of certainty, which is why often in weather forecasting, you have to mention the uncertainty, or you have to mention the confidence with which you are saying. And the confidence decreases the farther you are from today's time point. Now, let's start learning some basic definitions within probability. Some of I mean, most of these things you will be already familiar with, but I want you to stick with me because once we come to statistics, there are some interesting things, that insights that I want to share, which you may not have thought of earlier or prior to this. So probability is literally a measure of how likely an event is to occur. This is like the formal definition of probability. And as you know, it is denoted by P of E, where E is an event. It is number of favorable outcomes divided by total number of outcomes. So if we are describing an experiment by rolling of a dice, then an event is, let's say, a favorable outcome in a particular event is, let's say, getting even number after rolling a dice. This can happen in three ways. Either you get 2, 4, or 6. This means the number of favorable outcomes in this case are 3 out of total 6 possible outcomes: 1, 2, 3, 4, 5, 6. So P of E becomes, where E is even, so E equal to E1. P of E becomes 3 divided by 6, which is equal to 1 by 2. And remaining probability goes for odd. Now, in this case, there are a few terms which you can take notice of. Not a big deal, very simple. One is called sample space. Sample space is the set of all possible outcomes in an experiment. And here, if you are rolling a dice, you can have 1, 2, 3, 4, 5, 6. All of these are the possible outcomes. And if event E it is described by getting E1, then this event space is nothing but it will be a subset of the sample space S. So event space consists of all the possible occurrences which are favorable towards this event, which is E1. So it is 2, 4, 6. But if the event was described by odd, it will be 1, 3, 5. So these are fairly easy definitions. Now, let's look at some types of data. So the data that we will be dealing with in machine learning can be categorical data, non-categorical data, numerical data. So an example of categorical data is data like colors. So colors are, there are only certain number of colors described by English words, right? Red, blue, green, yellow, etc. So they are in categories. When we are devising a spam filter, if the filter is taking a decision that something is spam or not spam, it is also a categorical data, because if it is spam, the data is yes, otherwise it's no. So in categorical data, it need not be always numbers. It can be it will be simply described by some other either words. It could be true or false, etc. And here I have divided it into categorical and numerical data rather than categorical and uncategorical data. Uncategorical data are data that can be pretty much anything. So, for example, names of people. There are many different combinations, many different types of names for the people. Although it will feel like it is a categorical data, in my opinion, since the number of possible names for different people are so many in the world, it's not a numerical data, but it also is not a categorical data. So usually, if you remember, if you have heard of the famous Titanic dataset, it is nothing but a dataset of all the passengers who were traveling on the Titanic. In that, one of the data points is the name of the passenger. And while building a machine learning model to make a prediction whether, given the details of a passenger, if the passenger will survive the Titanic collision or not, the name is often discarded because name is not useful in that particular case, because name can be pretty much anything. Now, a numerical data can have discrete numbers as well as continuous numbers. So, for example, if we have 10 classrooms and we are talking about the total number of students in each classroom, it will be some number between 0 and, let's say, 100 or 0 and 200, depending on the strength of the total capacity of the classroom. So it will definitely be a discrete number within a range between 0 to some maximum value. So let's say classroom A has 40 students, classroom B has 67 students, and the next classroom may have 92 students, etc., etc. So these are discrete numbers within a range of, let's say, 0 to some max value. However, some numbers are continuous. So let's say we are describing the temperature inside a room like this. Then maybe the room temperature can only vary in this case if you have a cold AC versus if you have AC off in summer. Maybe the temperature can vary only from let's say 15 degrees Celsius to max, let's say 40 degrees Celsius. But although the range is very limited, the possible values that temperature can take are infinite, because temperature is described not just by these discrete numbers, it's described by real numbers. So 15.1, 15.003, it can be anything. So there are these continuous numbers. So if temperature is described as a variable, it can take any value, any of the infinite values between 15 and 40, any real number between 15 and 40. Right. So these are discrete continuous numerical variables. The previous one was categorical data. Okay, so I think we have touched upon basic things about probability. We'll be learning a little bit more complex and more useful things from probability in the next lecture. But I want to keep this as a basic introductory lecture to probability. Now let us move on to introduction to statistics. Why do we even have statistics? We have statistics because we can describe big data set using some representative numbers. So if you have data about the heights of 300 students in a class, and whether you want to decide whether the classroom on an average consists of tall students or not, you can define some central tendency like average height or median height, etc. So there are two tendencies that we are primarily concerned about in statistics. One is the measure of central tendency, meaning what is the most common occurrence in a collection of data. That is the measure of central tendency. And usually the most common central tendency definitions are using mean, median, or mode. The other tendency that we are interested is in the deviation, tendency to deviate from this central tendency. And that will be described by range, variance, or standard deviation. We'll come to that in a moment. So mean obviously is nothing but summation of all the entries in a particular data set divided by the total size of the data set. So that is mean. So if 1, 2, 3, 4, 5 is the data set, mean is nothing but 1 plus 2 plus 3 plus 4 plus 5 divided by 5. So it is 3. Median is nothing but the middle value in an ordered data set. So here the term ordered is very important to focus on, because let's say this is your data set. Here the middle value of this particular data set is 9. So you might be tempted to say median is 9, but median is not 9, because you have to order the data set. So here I have ordered in ascending order. Descending order is also fine. Both are fine. But in ascending order, here 5 is the middle point of the data set. So 5 is the median. But you had a middle point here because this was an odd data set. You had 1, 2, 3, 4, 5, 6, 7, right? You had 7 points. What if you have an extra point? Here I have added an extra 10. In that case, you have even, the data set size is even. So you have 8 data points. Then you will take the middle 2. Instead of taking the middle 1, you take the middle 2. And you can take an average of that. So this is 5 plus 6 divided by 2. So 11 by 2, 5.5. 5.5 is the median. So this is the definition of median. I will come to a very interesting example of why these things are particularly useful in using a very specific example. Now, mode is basically the most frequently occurring value. So in this data set consisting of 1, 2, 3, 4, 5, 6 numbers, mode is 20, because 20 is the most commonly occurring number in this particular data set. All right. I think these are good enough for the definitions of central tendency of a data set. Now let's take an interesting example. So I have a Google Sheets here. I'll open it. Okay. So let me first delete all of this. Actually, I don't have to delete. I'll just keep it. So what I have here is I have the name of 10 students. And I have their roll number 1, 2, 3 up to 11. So there are 11 students, and these students are taking 4 exams, exam 1, 2, 3, 4. All right. Now, maybe what I can do is I can take a screenshot and bring it to Miro, but probably let's keep it here for now. If needed, if I want to annotate, I'll bring it to Miro board. Now here, in these 4 exams, we have the marks scored by each of the students. So in the first exam, every single student scored 10. And assume that this exam was out of 100. So this 10 is not 10 out of 10. This is 10 out of 100, let's say. Exam 2, had a distribution like this. One student scored 100, one student scored 0, remaining students scored something in between. Exam 3 had this kind of a distribution, and exam 4 had this kind of a distribution, right? Now, using this example, we will understand why is mean, median, and mode important. So consider, let's maybe let's not consider this for a moment. I'm just hiding that so that you only focus on this. So in the exam 1, every single student had scored 10, which means mean is obviously 10. It's the average of all of this. Median is 10. It's the marks scored by the student in the middle. Student in the middle is Jessica. Jessica had scored 10. But student in the middle, we should not look at it in terms of roll number, okay? We should be looking at it in terms of the increasing or decreasing order of marks. In this case, there is no increasing or decreasing order. That's why I just picked Jessica here. But otherwise, anybody can be the median here. And mode is the most commonly occurring number, which is 10. So mean, median, mode is fine in this case. Now, how about this? In this example, in the second exam, we have scores ranging from 0 to, actually, let me do Control Z. We have scores ranging from 0 to 100. So one student has scored 100, and but many students have scored like this. Now, I have a question here. Let's say this score, instead of 100, this was 20, right? In that case, you can see that mean is 10, median is also 10. Mode does not exist because for mode to exist, there has to be some repeating value. So if two students had scored the same score, let's say this student and this student had scored 10, then we can say that mode is 10. But that is not the case here, which means mode is non-existent. But mean and median are the same. Now the question is, if we have a distribution like this, which one might be more useful? If there is if there is a tendency for huge deviation, sometimes median might be more useful than the mean. And here's the reason. So let's say Christopher, instead of scoring 20 out of 100, he scored 100 out of 100, which means he single-handedly increased the mean of the class. If Christopher had scored 20, the mean would have been 10. But now the mean has it did not double, but it has increased by 70 to 80% because Christopher has scored 100 instead of 20, right? So, but still, if you look at the entire class, the performance of the rest of the students have not changed. So collectively, if you take the entire data set of the class, just because one student has changed his data or his score, you are saying that now the mean is, instead of 10, it's 17. So mean in this particular case is not a great measure of like the average tendency of the class, because on an average, the class has performed somewhere around 10 only. Christopher was an exception. Now, if such an exceptional data set occurs, is it wise to describe the data set using mean? Not necessarily. So that is where median is helpful. Because here, if we look at median will be 10, because this is an increasing order of numbers. And in that, the middle comes this for Jessica, 10. So median is 10. And median is, in fact, a better measure of the central tendency of the class instead of mean in this particular example. So this is why we have different types of statistical descriptions. Now, let's take another example. In this case, you have students have scored only 2 types of scores. Actually, 3. Jessica has scored 20, let's say. Actually, you know what? I'll make this in such a way that, okay, so here there are 1, 2, 3. 3 students have scored 30. 1 student scored 20, and remaining 7 students scored 0. Now, if you take mean and if you try to calculate mean, basically it is 30 plus 30 plus 30, 90 plus 20, which is 110. 110 divided by 11, which is 10. So mean is 10. So mean in the first exam is 10. In the third exam also is 10. So if you simply keep looking at the mean, you will feel like, oh, the class has performed pretty much in the similar way. But that is wrong. That is not true. because the performance of the class is completely different in this exam versus this exam. So mean cannot describe the average performance of the class. How about median? Can median describe the average performance? So if we order this, we will have, because we cannot simply pick Jessica right now, because we have 11 numbers, and if we order it, it will be like this, right? We have 7 zeros. So we have to put that many 1, 2, 3, 4, 5, 6, 7 zeros, then 120, and then we have 330, if I remember correctly. So this is how the ordering is. And the middle marks is 1, 2, 3, 4, 5. 1, 2, 3, 4. I think this is the middle, right? Here on the top, you have 4. How many are there? 330, 120, and 3, 4, 5, 6, 7. 7 zeros. So 1, 2, 3, 4, 5, 6. We need one more. So median would be this guy. So 0 will be the median of this distribution. So 0 also, so median in this case is luckily able to capture the fact that many students have scored 0. But and mode is also able to capture that. So mode is 0 in this case. So this is what makes the median and mode more useful in this case, because if you are looking at the mean, you might be tempted to conclude that, oh, exam 1 mean was 10, exam 2 mean was 10, so exam 3 mean is 10, so exam 1 and exam 3 were similar. It's not at all the case. In exam 3, maybe there were only 3 questions, and students, those 3 questions were extremely hard, and some students managed to solve some questions correctly, but remaining students did not manage to solve any question. So the exam was not conducted in a good way. We can conclude that by looking at the data set or by looking at the median and mode. We cannot conclude that by looking at the mean in this particular case in comparison to exam 1. Now, what about exam 4? In exam 4, the marks are distributed like this: 0, 0, 0, 0, 10, 20, 20. So we have 1, 2, 3, 4, 5 people scored 20, 5 people scored 0, and 1 person scored 10. In this case, again, mean is 10, because if you can do the formula. I have already inserted the formula here. Mean is 10. Median is also 10, because the middle value is this 10. So median is also 10. But mode, there are 2 modes, 0 and 20. So it's like a bimodal distribution, because 0 is occurring 5 times, 20 is also occurring 5 times. So 0 and 20 are the mode. Now, again, if you compare, let's say, exam 4 with exam 2, if you look at median, you might be tempted to conclude that, oh, exam 2 and exam 4 are very similar. But that's not true, because exam 2 has like a range of distribution. But exam 4, students scored only three types of scores, either 0 or 10 or 20. So in this particular data set, mode is a better way to describe the data. So this is an example to show you that depending on the type of data set, sometimes mean is more useful, sometimes median is more useful, sometimes mode is more useful. It entirely depends on the data set. So that's the reason why people have defined these 3 measures of central tendency. Now let's take another example. Okay, here let's say some voting is happening, and the school is voting for students from this class based on roll number, right? So let's say the school has how many students? Here you have 200. Let's say the school has 181 students, and what the students are doing is they are voting. Actually, there are 200 students, I would say 200 or something, whatever. There are many students in the school, and they are trying to vote who should be let's say, the school leader. And the voting is such that the voting is based on roll number. So the student will pick. So if I am voting, my name is not here. I'm not contesting in the election, but I'm voting for one of these people. So if the voters, let's say my roll number is 12, I am voting for the candidate whose roll number is 11, meaning I am voting for Christopher. And let's say your roll number is 13. And if you're voting for this candidate 9, whose roll number is 9 is Andrew, right? So so here I have created a random set of numbers. And now we want to kind of figure out who won the election. So usually what we do in an election, whoever got the maximum number of votes is the winner, right? So here, if we calculate the mode of this distribution, I have already calculated it. So there is a function called mode on Excel. we can calculate the mode of this distribution, and it comes out to be 2. So meaning whoever has roll number 2 is the winner of this election. So that is Emily. So according to mode, if mode was taken as the measure for the success in an election, meaning the maximum number of occurring occurrences, then Emily is the winner. But what if it was median? The median of these set of numbers, which I have calculated using the formula again. So the formula is equal to median of, then you put the range. Median of this distribution is 5. So if we were to say that, okay, the median, which is the central tendency, right? So mean, median, mode, all of them are central tendencies or tendency of a group. Now, if we were to say that the tendency of the voter group is described, if it is described by mode, then Emily is the winner. If it is described by median, the roll number turns out to be 5. And who is 5? 5 is this person, Daniel. So then Daniel is the winner. And if we are saying that mean is the measure of success in a voting, then mean is 5.72, which we can round it off to 6. And who is 6? 6 is Jessica, which means if we had taken mean, then Jessica is the winner. But in elections, we use mode, right? Because whoever gets the maximum vote is the winner. So in this case, considering this is like a normal election, Emily is the winner. So these are the different ways in which we can measure central tendencies, and in some cases, one of them is more useful than the other. Now let's get back. I want to now touch upon briefly on the measures of dispersion. Dispersion meaning the variation from the central tendency. And there are 3 measures for that: range, variance, and standard deviation. Range is nothing but the maximum minus minimum value in a ordered data set. So this is 1, 2, 3, 4, 5. It's ascending order. It can be descending order also, but whatever the data set is, fine, pick the maximum value, pick the minimum value, and subtract those two. That's the range. So range in this case is 4. Variance and standard deviation are closely related. Standard deviation is just the square root of variance, but variance is defined as its symbol is sigma square equal to sigma over all the data points xi minus mu the whole square divided by n. Now xi is each of these individual points. Mu is the mean value square. You have to square them so that negative values won't cancel each other, and then divide by n. So what is the value here? So sigma square we can calculate. So mu is 3 because average of these set of numbers is 3. You can easily calculate it, or you can simply see that 5 plus 1 is 6, 2 plus 4 is 6, so 6 plus 6, 12, 12 plus 3, 15, divided by 5 is 3. So mean is 3. So you do xi minus mu. So 1 minus 3 the whole square, 2 minus 3 the whole square, 3 minus 3 the whole square, 4 minus 3 the whole square, 5 minus 3 the whole square. And you sum all of that. So minus 2 square, minus 1 square, 0 square, 1 square, 2 square. Then you can calculate this to be 4 plus 1, 5, 5 plus 5, 10, 10 by 5, 2. And the standard deviation is nothing but square root of this, and square root of 2 is 1.414. So this is how you calculate the deviation, the tendency to deviate from the central tendency. Central tendency, in this case, we are taking it to be mean. Now, before coming into data visualization, I also want to talk a little bit about the deviation, right? So now we were talking about exams. So let's say the exam marks are as following. Exam 1, everyone scored 10. Exam 2, people scored from 0 to 20 in steps of 2. In exam 3, people scored like this. 1, 2, 3, 4. 4 people scored, 3 people scored 30, 1 person scored 20, remaining people scored 0. Now, if we were to describe the performance in this exam only by mean, let's say, we were saying mean is, now I'm taking mean as the measure of central tendency, then the mean in all these cases, for this exam, mean is 10. For this exam, mean is 10. You can calculate it, but otherwise you can fairly easily see that in this exam also mean is 10. Now, mean alone is not sufficient to see whether an exam is a good exam or not, right? Now, this is where the tendency to deviate from the mean is also needed. If I wanted to describe the performances of this entire class by, let's say, 2 numbers, those 2 numbers are central tendency, the tendency of the data set, the central tendency of the data set, and the tendency of the data set to move away from that, let's say, central mean or central mode or median, whichever is our central, whichever is the measure of the central tendency, overall tendency of the data set. So my goal is to describe this data set just by two numbers. One is the central tendency and one is the tendency to deviate. So let's say I define that mean is my central tendency. Then I have 10, 10, and 10. So mean alone is not sufficient. Now let's look at a simple deviation. Simple deviation is nothing but how much this particular score is deviating from the mean. So in this case, all the scores are 10 and all of them are exactly same as the mean, which means the deviation from the central value is 0. So if this is a simple deviation, I'm not even talking about standard deviation or variance here. This is simple deviation. What about variance? Let's think about. Okay, once again, let's think about simple deviation. So in this case, if we had a simple deviation instead of variance, then the simple deviation is nothing but this equal to this minus mean, right? And I just need to put a symbol here. So now, if we look at a simple deviation, we can see that this is the deviation of this person from the central tendency of 10 is minus 10. Deviation of this person, Emily, in exam 2 from the central tendency of that particular exam is minus 8, minus 6, minus 4, etc. So simple deviation is not enough. Because if we add up all the simple deviation, we are getting 0 in this case. So from this, you will conclude that, oh, the mean is 10, the deviation from the mean is 0. That is not true, right? Because there is deviation from the mean. So maybe we can take absolute value, which is a good thing to do. But often, instead of taking absolute value, a better thing to do is taking square. Because if you square something, you can get a positive number. So what we can do here is, here we can define it to be the deviation from the mean raised to 2. So if we do that, let me apply it to all the data points. It is not a simple deviation anymore. It is variance, right? So variance is now summation of all of this, which is 40. Now you are saying that the central tendency is around 10, but the variation is 40. That also does not make too much sense. The reason why variance is not the most useful thing is because here you are saying that from the central tendency of 10, it can vary to the positive side by 40. It can vary to the negative side by 40, kind of, sort of. But to the negative side by 40 does not make sense because the minimum amount of marks a student can score in, at least in this exam, where there is no negative scoring, is 0. So the variance does not make extreme sense, which is why square root of variance, which is square root of 40, 6.32, makes much more sense in this particular case. So the standard deviation here is 6.32, and the central tendency is 10. The standard deviation in the first example was 0 because square root of 0 is 0. So here I will write. So this first number is variance. Second number is standard deviation. Variance, standard deviation. Now, how about this exam 3? In exam 3 also, mean is 10. And if we take a simple deviation, so let's say, let's not square it. Let's just take a simple deviation. Then we can see that simple deviation is as follows. The first guy is deviating from mean by 20. Second guy is deviating from mean by minus 10, by 20, minus 10, 20, etc. Right? So those are these numbers. Now, again, if we add up all the simple deviation, it is coming out to be 0. So we are now again saying that if we simply take a simple deviation without squaring it up, we are saying that the exam 3 marks are, exam 3 performance is very similar for the class compared to exam 1. But that's not true, which is the reason why we have to take square so that we have the variance. Now, if we calculate variance is very high here. Variance is like 181. But 181 is like having a central tendency to be 10 and tendency to deviate to be 181. It's not extremely insightful. So we take a square root of this. So then we get standard deviation. Standard deviation is 13 in this case. So mean is 10, standard deviation is 13. Don't wonder, like if you are wondering like, oh, how does this measure the negative tendency, in the sense like tendency to be on the left side of 10? Are you saying that towards the left side it can go to minus, because 10 minus 13 is a negative number? Are you saying that now there is a tendency to go to negative marking, negative scoring? No. there is no such thing. This is simply an artifact of the data set, but this is a much better measure. The standard deviation is a much better measure of the tendency to deviate. Now, if I were to describe the performance of the students using two numbers, I will say one number is mean and the other number is standard deviation. So the mean in the first exam, mean is 10, standard deviation is 0. In the second exam, mean is again 10, standard deviation is 6.234. In the third exam, mean is 10 and standard deviation is 13.4. And it makes sense because in the third exam, you can see that there is much more variance. The score goes up to 30. In the exam two, people were scoring kind of close to each other, but there was a range from 0 to 20. Now, if we were to mention the range in this case is 10. It's 10 minus 0. Range in this case is 20. Range in this case is 30 minus 0, which is 30. So range also is not the best measure to capture the variation in this case. The best measure in this case is standard deviation. So this is why people have also defined these tendency to deviate from the central tendency. Now let's come to the last part of today's lecture. It is data visualization. This is fairly simple, straightforward. We can visualize data in different formats. And data visualization is extremely important because often whatever statistical things that we can see, we are coming up with, let's say it's a mean or standard deviation, etc. Instead of looking at the numbers, we can also see that visually. So often you might have seen like a distribution that looks something like this, a distribution that looks like this, right? And here you will say that the mean is whatever is the value of the middle. So here the mean is 0 and standard deviation is the width of this distribution, right? And how do you say that? You're saying it kind of visually. So giving a graph like this and graph like this can help you outright say that without even looking at any numbers, you can say that the mean of these two distributions are the same, but the standard deviation or the kind of the range of values that the two are spanning. When I say range, I don't necessarily mean max minus min in this case. I simply mean kind of the spread of the data set. It's much more in this particular curve. The spread of data is much less in this particular curve. And how are we saying that? How can we say that without even seeing any single number, simply by looking at the data? So data can tell story. If you are a data scientist, which is an important part of doing machine learning, data visualization is something that you have to master. So let's take a simple example here. So you have 5 students, with student ID or roll numbers 1, 2, 3, 4, 5. And we have the scores that they had from 2 exams, math and science. Now let's look at the usefulness of different plots here. So if you were to plot a bar plot of student ID on x-axis versus score on the y-axis. So this is ID and this is score. And let's try to plot, right? So I will use black color for math. So I need rectangle basically. So let's pick a rectangle. So this is, and then we can fill some color. So let's say black is, so in the first exam, math score was 45. And science score was 50. So we can put it like this. Oh, 50 is higher. So, and the color for science could be, let's say, red. Then again, I will copy paste this. In the second exam, math score was 50. Science score was 60. And in the third exam, math score was 55. And science score was 65. Then 60, 70. So basically the exam scores are improving one exam after the other. So now it is 60. And this is this much. So it's 1, 2, 3. Then this is the last exam. Last student. And you have 65 and 75, right? Okay. So now in the x-axis, so this is basically a bar plot. And we have to define the legends. So legend can be defined simply like this. Draw 2 squares. And here you write science and math. So math is black in this case, so I can color this by black. And then science is red, so I can color this by red. So this is kind of how the data description looks like. And this is ID 1, 2, 3, 4, 5, right? So these two belongs to 1, these two belong to 2, 3, 4, 5. Now, bar plot was useful in this case. I'm not denying that. But often if you want to, if you have too many data points, now imagine you had 7 subjects, it's very difficult to keep track of things using bar plot. So that is the case when scatter plot is very useful. So scatter plot is essentially something that looks like this. So you have ID, you have score, and the science score is always, in all the exams, science score is higher. So science, I can plot like this. And math is slightly lower. So math is like this. So from this, and then for ease of all of this, I can simply draw like a dotted line, which is like a trend line connecting between these this data. I can draw the same thing. So here immediately it's easy to visualize, and the black circle is math, and the red circle is science. So both of these, and this is 1, this is 2, 3, 4, 5. So both these plots are telling the same thing, but this is called as a scatter plot, and this is called as a bar plot. So although both of these are saying the same thing, it's much more clearer, the degree of difference between math and science, and the fact that always students are scoring higher in science is much more clearer from this particular graph. It's also clear from this, but to my eyes, this is much more easy to do visualize. But bar plot is also often very useful, of course. Now, let's also look at histogram. So histogram is probably the most important graph that you will come across in the entirety of machine learning because of the sheer volume of data. So histogram shows you the tendency, the central tendency, as well as the deviation. So to get histogram, usually what we do is we have to define buckets. So here, look at the score range. The score ranges from 45 to 75. So we can divide this into 3. Let's say score ranging from 45 to 55, 55 to 65, and 65 to 75. And this is math, and this is science. Now let's look at how many students scored in the range of 45 to 55 for math. For math, 45 to 55. So I'm when I say 55, I'm not counting 55 here. 45 to less than or equal to 55. Okay. So here only 2 students, student ID 1 and 2. So 2 students scored in that range. So which means the number corresponding to this is 2. 55 to 65, how many students scored? 55 and 60. 65 is not counted. It's outside the thing. So only 2 students scored this. And 65 to 75, this is included. This is not included. Okay. So here it is like greater than or equal to 45, but less than 55. Greater than or equal to 55, less than 65. Greater than or equal to 65, less than 75. So we are bucketing. We are creating 3 buckets. And for math, only 1 student has scored in this range. What about for science? For science, we have 2 students in this range, 2 students in this range, and 1 student in this range. So now a histogram would look something like this. So we have 3 buckets. So this is bucket 1, bucket 2, bucket 3. And for math, the histogram would look like this. There are 2 students in the first bucket, 2 students in the second bucket, and only 1 student in the last bucket. And this is the histogram for math. Usually it's like you can draw it like as a continuous figure also. And for science, there is 1 student in the first bucket. There are 2 students in the second bucket. And there are 2 students in the third bucket. And this is science. So, and we can also define like an overall thing. So overall is like there are 3 students in the first bucket in this range. If you consider math plus science, there are 4 students in this bucket and there are 3 here. So overall could look something like this. This is overall for the first, Overall is actually like this. Overall, this is the first exam. This is the first bucket. This is overall how the second bucket looks like. And this is overall how the third bucket look like. So this is bucket 1, bucket 3, bucket 2. So this is bucket 1, bucket 2, bucket 3. Bucket 1 is the lowest scorers, bucket 2 is medium scorers, and bucket 3 is high scorers. So you can see that on an average, which is the blue curve, the number of medium scorers are highest, which is this. The number of low scorers and number of high scorers are low. But if you come to math, the high scorers are less. Number of high scorers are less. There are more students who are either scoring too low or somewhere in the middle. But when it comes to science, very low scorers are less, as you can see here. There are good number of medium range scorers and good number of high scorers. So these are the ways in which you can get meaningful insights from a data set. So this brings us to the end of today's lecture. We looked at probability, statistics, and data visualization. And in the further lectures, we will be continuing to learn but in much more rigor and much more detail. So please stay with me. Today was the start of a fresh module in this course. So I'm sure you will enjoy the rest of the modules also. In this probability and statistics modules, we'll have roughly 5 to 6 lectures. The exact number will depend on the recording. And I really want to congratulate you for starting this part of the course, because this is, first of all, one of the most important aspects which is related to machine learning. Plus, since this is a starting point as well, you can continue with me for the rest of this module. So thank you so much for listening. We'll see you again in the next lecture. Take care until then. Bye.